Good morning. Good morning. Can you hear me? Am I on air? Okay, so. Okay. Then, good morning and welcome to this lesson where we will have exercises using least squares with the manifold formulation that was introduced in the last lesson. So we will start with a very standard 3D Icp optimization. Then we will see registration with similarities, and finally we will see an exercise and the code that you have to modify in order to make this registration problem be solved. I said similarities, but I won't go deeper in details now because we will see this in the next set of slides. So in total, we will have 3 exercises. 2 of them will be already solved, and then you will have to solve the exercise for the 3rd exercise. In the first 2 exercises, the manifold will be only the state space will be non-Euclidean, while in the 3rd one also the measurement space will be non-Euclidean, so that you will be able to see both the box plus and the box minus in action. So, after this very brief introduction, let us start talking about Icp in 3D. Icp is formulated as follows. We have a set of points in the word frame, which we indicate by pi. And we have a corresponding set of measurements, of 3D measurements, in the robot frame. Assuming that the correspondences between these 2 sets of points are roughly known, then we can solve the problem of finding the transformation that minimizes the distance between corresponding points. In particular, we want to transform the points in the word frame, which we indicate by pi, in such a way that we minimize the distance with the measurements that are points in the robot frame. This means that we want to find the transform, which is the pose of the word frame with respect to the robot. Saying it differently, we want to find the transformation from the word frame to the robot frame, which minimizes the difference between the points in the word frame to which we apply this transform and the measurement which are in the robot frame. So we want to find the transform from the word frame to the robot frame that superposes the points in the word frame to the points, to the measurements which are in the robot frame. Now, we could also estimate the pose of the robot with respect to the word, but this would lead to longer calculations, as you will see in a second. Indeed, if we formulate the problem by that of finding the transform, which is the pose of the word with respect to the robot, minimizing the difference between points in the word frame and points in the robot frame, then the formulation is really straightforward, while it won't be so if we decided to estimate the robot with respect to the word. Now, let us have a quick look at the recap of the algorithm. Recall that in least squares, in iterative least squares, we iteratively minimize a nonlinear cost function by considering its quadratic approximation around the current estimate of the state. In particular, what we do is we build the H and B matrices, which are the coefficients of a linear system, from which we compute the perturbation delta x, which is then applied to the current estimate of the state to improve it. Now, the matrices H and B are computed summing the contribution coming from each of the measurements, in particular according to the two formulas that you see here, where the H matrix is composed by the sum of J transpose omega J, while the B matrix is composed by the sum of J transpose omega E. Now, in this exercises, we will focus in particular on the manifold formulation. You can see the manifold formulation in action, in particular in the computation of the error function, in the computation of the Jacobian, and in the computation of, and in the application of the perturbation to the current estimate of the state. Indeed, when the measurement space is a manifold, so it's a non-Euclidean space, then we compute the error function by taking the box minus between the prediction of the measurement and the actual measurement instead of the regular minus. Recall that box minus means that we compute the manifold around hi of x star and then project zi into this chart. We compute the chart around hi of x star. We project zi onto the chart and measure the difference on the chart between hi of x star and zi. We can see instead the box plus in action here, where we have that the update of the state is obtained by performing the box plus by a perturbation vector, which is obtained at the solution of the linear system to the estimate of the state. Now, box plus means instead that we compute the chart around x star and move on the chart by delta x, then get back to the manifold. Okay, this is all things that you already know, but if there are any questions, feel free to ask. And if there are not, then I can move to our specific problem again. So, let's talk about the methodology. In all the times we want to formulate these least squares using the manifolds, then we need to define the state space, the measurement space, and the prediction function. As far as the state space is concerned, we need to qualify the domain, which might be a Euclidean one, R2, R3, or a non-Euclidean domain, such as ST2, ST3, or also S2, as we will see in the last exercise. After you have qualified the domain, you need to define a Euclidean parameterization for the perturbation. The Euclidean parameterization will be the domain of the chart, of the perturbation which lies on the chart. After having defined the Euclidean perturbation, we also need to define the box plus operator. In particular, the box plus operator should be such that when the perturbation vector is 0, then the box plus operator corresponds to an identity. Because if the perturbation is 0, the displacement is 0, then when we move by delta x, which is 0 on the chart, we should stay in the point where we started from, in x. Say if we have x box plus delta x. Having said so, we can talk a little bit about the measurement space. Again, we need to qualify the domain, which might be Euclidean or not. We need to define a Euclidean parameterization for the perturbation, which in the end will be the domain of the displacements lying on the chart. And then we need to define a box minus operator. Why is that? Because as you can see from the previous slide, the measurement space, when the measurement space is an element of a manifold, then the error function is computed using the box minus operator, which again, recall, that means measuring the distance on the chart between the projection on the chart of Zi and the projection of the chart of Hi of x. In particular, the chart is computed around the first operand of this box minus operator. When we are done with this, we can identify the prediction function. The prediction function is the function which allows us to predict the measurement given the current estimate of the state. In the case of the ICP problem, then what we have is that the prediction function should allow us to predict the measurement, that is, to predict the pose in the robot frame of the given points in the word frame, given the current estimate of the pose of the word with respect to the robot. But we will see this in a second. It was just to give you an example of a prediction function. If everything is clear so far, I can move to our specific problem. Okay, are there any questions, or do you feel uncomfortable with this? No. Okay, so I guess I can move on with today's problem, that is ICP in 3D. So in this case, the state is an element of the special Euclidean group of dimension 3, which again is composed by, it's a homogeneous transform composed by a rotation matrix and a translation vector. And as a Euclidean parameterization, we can consider an element of R6, as we have seen also in other exercises. Now, as far as the box plus operator is concerned, it is convenient to use the vector to transform function applied to delta x, because the vector to transform function applied to delta s returns a transformation matrix which is equal to the identity when delta x is equal to 0. And this is the fundamental property that you need to check when you choose a box plus. Again, the box plus operator should be chosen such that when the perturbation delta x is equal to 0, then the box minus operator should correspond to an identity operator. You can easily check this because in this case, for example, when delta x is equal to 0, then delta alpha is equal to 0 as well. Then R delta alpha is the identity. And delta t is equal to 0. So that here you have that when delta alpha and delta t are equal to 0, then x box plus delta x is equal to RT, which is exactly x. Having said so, we can move to the measurements. Now, in this case, measurements are Euclidean, belong to a Euclidean space, to the set of vectors of real numbers of dimension 3, R3. so that we do not need to define a box minus, which will be substituted in the algorithm that we have seen a few slides ago by a regular minus. Now, in the computation of the error, you have seen that we have hi of x box plus delta x minus z. So let us expand hi of x box plus delta x using the formula that you have here. Then this gets to x box plus delta x pi. And then by substituting the expression of x box plus delta x, you get this expression for h of x box plus delta x. I first explain the meaning, and then if there are any questions, please go ahead. So, in this case, the prediction function is given by x pi, so it's the application of x, of the transformation x to the point pi, because our state is the transformation from the word frame to the robot frame. And as the prediction function is the function which allows us to compute the predicted measurement given the current state, and given that our measurements are point in the robot frame, then in order to predict a measurement, that is, predict a point in the robot frame, given the point pi in the word frame, what we do is we apply x, which is a transformation from the word frame to the robot frame. Differently said, multiplying pi by the state x allows us to predict the pose of pi in the robot frame. And since measurements are positions in the robot frame, then this is exactly what we need in order to predict a measurement, or in order to predict a point which can be then compared with a measurement. Is that clear? Yes, okay. And the classroom, they seem to be happy with this. So, I am moving on with the error function. It is very simple because, again, the box minus is a regular minus because the measurement is a Euclidean vector. So again, the error allows us to compare the predicted measurement and the actual measurement. Measurements are points in the robot frame, while points pi are points in the word frame. So what we do is we apply the transformation from word frame to robot frame to predict the measurement, and then compare it to zi. Okay, recall that with the notation pi prime, we mean the point pi in the word frame transformed into the robot frame. So it's a pi where we have applied the transformation from word frame to robot frame. Okay, now, rotation matrices. This slide is for recalling that a rotation matrix can be decomposed into the product of a rotation matrix along the x-axis, the y-axis, and the z-axis. And it is also to give you a quick reference to the derivative of these rotation matrices and to the values of the derivatives in the angle equal to 0, because we will be using this in the computation of the Jacobian. Okay. I move on with the Jacobian, where we will stay a little bit more on. So, As you have seen in the algorithm, in the computation of the Jacobian that we need is the derivative of the error computed in x box plus delta x with respect to delta x computed in delta x, which is the perturbation, equal to 0. Now, such Jacobian is as high as the error, which is three-dimensional, because again, measurements and then the error as a consequence belong to R3. And it is, this Jacobian is as large as the number of variables. Now, the variables are 6, because we have seen that the Euclidean parameterization of the state domain is R6. Delta x has dimension R6. And therefore, this Jacobian is 3 times 6. Then, once you're convinced of this, then you can move on with the calculation. In particular, we can split this Jacobian into the derivative with respect to delta t and the derivative with respect to delta alpha. Now, both these Jacobians are dimension 3 times 3, because they are as high as the error and as large as, respectively, delta t and delta alpha, but both of them are dimension 3. Then we can move a step further, and recalling that the error is r delta alpha pi prime plus delta t, and that pi prime does not depend neither on delta t nor on delta alpha, then we have that the derivative of the error with respect to delta t is equal to the derivative of delta t with respect to delta t, because r delta alpha pi prime does not depend on delta t. And equivalently, delta t does not depend on delta alpha, so that the derivative of the error with respect to delta alpha is given by the derivative of r delta alpha pi prime with respect to delta alpha. Then, if this convinces you, you can further move on and then split the derivative with respect to delta alpha in derivative with respect to delta alpha x, delta alpha y, and delta alpha z. This is just a matter of computation, okay? The important thing is that everything is clear up to here, up to the third equality. Then the rest is just regular algebra analytics computations. So anyway, at this point, you make the same consideration as before. So what you say is that r delta alpha y and r delta alpha z do not depend on delta alpha x, so that the derivative of r delta alpha with respect to delta alpha x is indeed the derivative of r delta alpha x pi prime with respect to delta alpha x. And this is because r delta alpha is the product of r delta alpha y, r delta alpha x, r delta alpha y, and r delta alpha z, so that you can go and apply the usual formula that the derivative, concerning the derivative of the product, according to which the derivative of the product is the derivative of the first term times the other non-derived, plus the derivative of the first term non-derived times the other term derived, and so on. So let us focus just on the first one. And always recall that we are computing this in delta alpha x equals 0. This is fundamental. So let us focus for a second on just the derivative of r delta alpha x with respect to delta alpha x. Then you go back to the previous slide, and you see that you have to consider this particular matrix here, 0, 0, 0, 0, 0, minus 1, and 0, 1, 0, which gives you, multiplied by pi prime, 0, minus pi prime z, and pi prime y. Now, if you assemble these three vectors here, where you need to use this rotation, and this rotation, then you will easily get that these three vectors here assemble into the minus the skew-symmetric matrix in pi prime. They can be compactly written as minus the skew-symmetric matrix of pi prime.
So those are Rx, Ry, and Rz, not all the others.
It's an Rx delta alpha x, if you want to see, because it's yes. So the question is, so this R here, these three are Rx, Ry, and Rz, and not only R. And the answer is yes. If we want to be very precise, then this one here is an R. But these three here are Rx, Ry, and Rz respectively. Yeah. Okay, you should do that on paper to be even.
Observe what R means. R is a rotation matrix of a perturbation. Okay? The perturbation is evaluated in 0. R is the multiplication of three matrices, Rx, Ry, Rz. Now, if I'm differentiating with respect to Rx, this means that I'm calculating the derivative of the rotation matrix in X and evaluating all and multiplying by two identities. Therefore, in this block, in the first block, you only find the R prime, because the zero perturbation results in the identity. So you find only R prime of X in the first column, in the first, block, which multiplies P. R prime of Y in the second column that multiplies P, and so on. So, sorry.
Yes.
It was a tricky thing. It's fantastic, because when you multiply with P, you discover what happens.
Yeah, we were very compact here, and your colleague is right that this should be an Rx according to the notation of the previous slide. I would suggest you to be even more specific and write down all the passages, noticing that delta x is equal to 0 in our computation. That is the important thing. Okay, so now let us go to the code if there are no more questions. Here you can see the vector to transform function, where you can recognize that we are multiplying Rx, Ry, and Rz to obtain the R matrix, the R without any specification. And then you have the vector, the first three elements of the vector, which become the translation part of the transformation matrix T. Then you can see the error and Jacobian function, which takes as input the current estimate of the state, a measurement z, and a point in the word, and computes the predicted measurement by applying the transformation to the point in the word to obtain a point in the robot frame. Then we compute the error as a difference between the predicted measurement and the actual measurement. And then we write down J as the composition of two blocks. The first one is the identity, and the second one is minus the skew-symmetric matrix in the prediction of the measurement z hat. In this other slide, you have the usual Icp computations. In particular, you have that x is initialized to its x guess, to the initial guess. Then you have a vector key stats, which collects the statistics of the key value. And then you have a for loop over the number of iterations of the Icp, of the least squares problem. And then you have that for each of these iterations, we build the H and B matrix, summing up the contribution of all the measurements Then finally, we compute the perturbation, solving a linear system with coefficients h and b. And in the end, we apply this perturbation to the current estimate of the state. Notice that we are not using the regular plus, we're using the box plus, which in this case is a vector to transform function. Okay, if there are no questions, we can move to see how this code runs and move to a discussion about the outliers and the robust kernels before moving to the next exercise. So, do you have any questions? Okay. In class, everything seems okay, so I will move to the testing part, and I will show you the code. So, code. Let us start with the script, which is called the Icp 3D no manifold versus manifold. As you can see, we are spanning a set of points in the word frame using the random function. We are defining a ground truth for the word to robot transformation, and we are computing the measurement, which are points in the robot frame, by applying the ground truth transformation to the points in the word frame. At this point, we have the set of points in the word and the corresponding set of measurements, which are generated synthetically. Now, you have this line which is commented out for you to try later, which is an addition of noise to the measurements, okay? Then finally, we have the number of iterations, which is set to 100, and we have a set of vectors which collect the value of the key and the value of the inliers. Then we have two instances of the least squares problem, one with a good initial guess and the second one with a bad initial guess. This is for you to see the difference between doing ICP without and with the manifold formulation. While the two solutions will be, the two evolutions of the key value will be similar with and without the manifold, when we have a bad initial guess, then you will see the difference between using or not the manifold very well. So here, octave Icp 3D no manifold versus manifold. Okay. Now it takes a second to make the computation. And then, okay. So as I was anticipating, with the good guess, you cannot see a big difference between the use of the manifold formulation or not. While with a bad initial guess, then you can see the difference between using or not the manifold formulation. And of course, this difference amplifies when you introduce noise on the measurements. So I have presented you this code so that afterwards you can try it out with different values of the noise and applying noise to the measurements. Here you have figure 1 and figure 2. Again, you can see the evolution of the key, which is error transpose times error as the iterations goes on. And you can see the difference between using or not, again, the manifold formulation. Okay, so now let us move again to the slides and talk about outliers. In real-world problems, data association might fail so that we generate false associations. measurements that are characterized by these false associations are called outliers. We can recognize the outliers because the key for these measurements is much higher than the key for the other measurements for which the association is good, in which case we talk about inliers. So points corresponding to wrong associations are called outliers, while good points are called inliers. We can see the effect of outliers in the value of the key by looking at the value of the key as the iterations goes by, as we will be doing in a second. So let us move to the code for a second. Again, this time we are moving to the script, which is called Icp 3D Statistics. Again, we are spanning a set of points in the word frame and the ground truth position of the word with respect to the robot. Correspondingly, we are generating the measurement. Then what we do is we start from a bad initial guess, always use the manifold formulation, and add an increasingly higher percentage of outliers. Now, as we are generating the set synthetically, the set of measurements synthetically, there is no way that we compute wrong associations because we have an ordered vector and then transform it through the ground truth transformation from the word to the robot frame and get again an ordered vector Z. So again, no way that we make a wrong association. So what we can do in this simulated example to introduce outliers is we change some measurements. So in this for loop, we inject an increasingly higher set of wrong points, and what we do is we simply substitute the measurements corresponding to the application of this transformation to the points in the word frame by, again, random points. Now, if you run this script, which is called, again, Icp 3D Statistics, so octav, Icp 3D Statistics, you can see that here it is. The evolution of the key square is not really encouraging because we have 0 with 100% inliers. But then, as the number of inliers reduces and correspondingly we increase the number of outliers, then the key value increases correspondingly. So that we have 12 12 key square value in the case of 50% outliers. Yes? No, probably it's 25. It's 25, actually. 25% outliers. Anyway, you can check by yourself. But the important thing is that we can do something about this. And in particular, we can use robust kernels. And again, back to the slides. As I was mentioning, you can recognize that the point is an outlier because the error is bigger than a given threshold, and in any way much bigger than the error associated to inliers. So what you can do is you can lessen the contribution of these measurements. Now, you have seen more sophisticated robust kernels, but in this example, we will stick to the case in which we say that if the chi-square is bigger than a given threshold, then we keep the error as big as this threshold. So we keep the chi as big as this threshold.
So basically we scale it down, but we keep this direction.
Yes, we scale it down, but keep the direction. If this check is false, then what we do is we say that we have an inlier, so increase the number of inliers for that particular iteration. Now, from the code, from the code I ran before, it also produces this error with robust kernels, which is much better than the error without robust kernels that we have seen in the previous, say, a few seconds ago. Okay, so this is the same plot that I already shown you using the Octave script. So we can move to the conclusions and say that using manifolds does not make the derivation more complex. Indeed, we just introduced a vector to transform function in order to apply the perturbation rather than a regular minus. Convergence is usually improved. We have seen that in particular with a bad initial guess, convergence is much better when we use manifolds. We have seen robust kernels that again might help in case of outliers. And in conclusion, we recommend that you try out these scripts and change the values of the noise in order to understand what's happening. Okay, so if this is clear, then we can move to another exercise, to other two exercises actually. They are, especially the first one is very similar, so if this was clear, it should not be so much difficult. Okay. So, let me take the next set of slides. Here. So, in this set of slides, we will see registration on a manifold. In the first example, we will consider the very same problem as in the previous exercise, but we will consider the scaling as well. So, points in the robot frame will be obtained from points in the word frame through a rigid transformation and a scaling. In the second exercise, instead, we will be dealing with measurement space, which is non-Euclidean, and I will go deeper in details further. So again, the problem in this case is that we have a set of points in the word frame, we have a set of measurements in the robot frame, and assuming that the correspondences are roughly known, we want to find a transform that minimizes the distance between corresponding points. Again, the transform will be the transform bringing the points from the word frame to the robot frame, because measurements are expressed in the robot frame. So, the transform we're looking for will map the word in the robot frame, and in this case, we will be considering not only a rigid transformation, but also scaling. So, if we assume that points in the word frame can be mapped to points in the robot frame through both a transformation of a rotation matrix R and a translation vector T and a scaling, then SC3 is no longer sufficient to represent our state. We need a different group. We need a group which is able to represent the scaling as well. This group is the group of similarities. We indicate as sim3 the group of similarities in 3D. Now, similarities are a group just as SC3, meaning that we have an identity term, an identity element which is again the identity. In 3D, it's a four-dimensional identity function. And elements of this group, just as elements of SC3, can be composed by multiplying them. In particular, we need to mention that S equal 1 corresponds to no scaling, S bigger than 1 to zoom in, and S smaller than 1 to zoom out. Now, let us define the perturbation vector, a Euclidean parameterization of the similarity group. In this case, defining a Euclidean parameterization is more tricky because we need to find something that allows us, as usual, to have that when we apply a perturbation which is equal to 0, then the element x stays where it is when we do x box plus delta x. So we need, given that the identity for the scaling is 1, then we need to find something which is 1 when delta s is equal to 0. And the function which maps a 1 to a 0, it's a logarithm. To be even clearer, we want to define a perturbation in such a way that when we do x box plus a vector of 0, then we still have x. And in order to do this, one possibility is to define the vector to similarity function as a function which returns you a similarity matrix, a similarity that has as rotation matrix R delta alpha, as translation vector delta t, and as scaling the exponential of delta s. In this way, when delta s is equal to 0, then the exponential of delta s is equal to 1, then we have the identity. V2s of delta x when delta x is equal to 0 returns an identity, meaning that x box plus delta x with delta x 0 vector is again x. Okay, if this is clear, then everything is very simple in this exercise. So let me know if this is clear, if this makes sense. Yes. So the two students in class are happy, so we can...
Everyone is happy.
So everyone is happy. No, sorry. Sorry.
Which is probably me. So.
Okay, so, but please write on the chat if you have any doubts. Okay. So then now let us move to the measurement function. It's really simple because we have points in the word frame indicated by pi, and we want to get points in the word frame, in the robot frame, because measurements are in the robot frame. The mapping from the word frame to the robot frame is given by the transformation x box plus delta x, so that the function which returns us a measurement given the current estimate of the transformation from the word frame to the robot frame is the following: x box plus delta x times pi. Now, having defined x box plus delta x using the vector to similarity function as in the previous slide, then you can easily derive this formula here, where x box plus delta x pi is equal to the exponential of delta s applied to r delta alpha pi prime plus delta t. Let us go a little bit deeper into this. So you can recognize that what you're doing is you are computing the point in the robot frame corresponding to the point pi in the word frame by applying the similarity x. Applying the similarity x means rotating pi by r, translating by t, and then scaling by s. Then, having defined the vector to similarity of delta x as a similarity which has r delta alpha as rotation, delta t as translation, and exp delta s as scaling, then applying this to xpi gives you this expression, where the point pi prime in the robot frame is rotated by r delta alpha, translated by delta t, and scaled by the exponential of delta s. Okay, this is the way you should read this formula. So the way you should read this formula is that you have the point pi in the word frame, you obtain the point pi prime in the robot frame by applying x, and then finally you apply the displacement by delta x, the perturbation delta x. And for the last time, recall that x box plus delta x means computing the chart around x, moving by delta x on the chart, and then get back to the manifold. Okay, so if this is convincing, then we can move to the derivatives. Are you happy with this? Yes. Okay. So, let us move to the derivatives. Again, the error is defined as the difference between the predicted measurement and the actual measurement. We have a minus because the measurement belongs to R3. Now, the Jacobian, which is the derivative of the error with respect to the perturbation computed in the perturbation equal to 0, is as tall as 3, because the error has dimension 3 as the measurement, and as large as as large as the dimension of delta x. But delta x in this case is 7-dimensional, because we have delta t and delta alpha as in regular ICP. But then we also have delta s, which is our 7th element of the perturbation vector. Now, if this is clear, then what you can do is you split this derivative with respect to delta x into derivative with respect to delta t, derivative with respect to delta alpha, and derivative with respect to delta s. Then again, here we are skipping some passages, but the derivative of the error with respect to delta t is given by the derivative of exp delta s times delta t, because the first term of this sum here does not depend on delta t. And as the Jacobian is being computed in delta x equal to 0, so also delta s equals to 0, then we have that the derivative with respect to delta t is the derivative of exp delta s delta t with respect to delta t, but exp delta s is constant with respect to delta t, and it is equal to 1 in delta s equals 0, so that in the end we only need to compute the derivative of delta t with respect to delta t, which is the identity. The very same reasoning holds for the second block of this matrix, of this Jacobian matrix, which coincides with the one of the 3D ICP, because again, the key passage is that here, that here you have that delta s it should be computed in 0, and the exponent exp of 0 is 1. So that when you go and do the derivative with respect to delta alpha, in the end it's a derivative of r delta alpha pi prime, which we already know how to compute. And then finally, you have the derivative with respect to delta S. Again, the derivative with respect to delta S is computed by saying that the derivative of the exponential is again the exponential, which computed in 0 is 1. So you have 1, which multiplies pi prime, and in the end, it's pi prime. Okay, of course, you should do it by yourself, maybe even more than once, to keep this in mind. And in the end, you will know this by heart after all the exercises. But if you have anything that you do not understand, then I will answer your questions. Okay. Can I move on? Yes. In your folder, you have the code which corresponds to this problem, and I think I will move directly to the code. So octave, 23 registration, similarities, and then go to code, and here. And here you have, in the geometry helpers 3D, as usual, the transformation from vector to similarity. But here in Icp 3D, you find the computation of the error and the Jacobian, and the usual do Icp function. In the computation of the error and of the Jacobian, you can recognize that we are extracting the translation vector, the rotation matrix, and the scaling factor out of the transformation x, which is the current estimate of the state. And we are using this to compute, to predict the measurement associated to the point P in the word frame. Then once we have the hat, we compute the error. Then we compute the Jacobian, which is a 3 times 7 matrix, where the first block is the identity, the second block is the skew-symmetric matrix in minus z hat, and the third block, which is indeed a vector, a 3-dimensional vector, it's simply z hat. In the do Icp function, which takes as input an initial guess, a set of points in the word frame, a set of measurements, the number of iterations, the damping, which eventually is added to the H matrix, and the kernel threshold. Then what you have here is, as usual, you have a set of iterations. So during each iteration, you build the H and B matrices, and then you use them to solve, they are the coefficients of a linear system from which you obtain the perturbation delta x. Once you have delta x, then you can update the estimate of the state by using the box plus operator. In this case, the box plus operator is a vector to similarity function. Notice, it is perhaps the first time that you see this, that we are adding a damping. Actually, we are not, because in the main function where we call this do Icp, we set the damping to 0. But in general, you could add damping here, which helps especially when the H matrix is badly conditioned. Okay, and you can also recognize the usual robust kernel implementation. This is a very simple one. You can do better if you want using the lesson about robust kernels. Okay, so said, if everything is clear, I can run the program and then move to the actual exercise, to the one that you should do by yourself. Okay, so while I run this exercise, you let me know if there are any doubts.
tone they're gonna see, and also here. Can you see, guys? Are you Falcons? Huh? Okay. I'm the only blind in the group. So with my phone.
Okay. So, the important thing is that we did the thing correctly, because you can see that the error goes down up to 0. And this is correct because we are using a synthetic data set, so no wrong measurements, so we expect no wrong associations.
Yeah, because, sorry, the guys have heard this problem already in the past, but they never have seen it develop. So now is the time for you.
Okay. So, okay, so as it seems there are no questions, then we have this probably last 20 minutes of explanation, and then you will do this exercise by yourself. Let's see. Okay. So, can I move on? Everything clear. Okay. In this exercise, we have points in the 3D space. As usual, we have points in the word frame in the 3D space. And we have a set of measurements. In this case, the measurements belong to a manifold and to a non-Euclidean space. Why? Because we assume that instead of having points in the sensor, in the robot frame, in this case we only have direction vectors of the points expressed in the reference frame of the sensor. Now, this is what happens for sensors like cameras. In the case of cameras, we have that points are projected to a camera image, and then when we unproject them, we have a direction, not a point. So this is for saying that this problem is a real one. It has important applications. And also for anticipating that in the next lesson we will see projective ICP, so we will be talking about cameras, so you will see calibration matrix and camera to word transformation and so on, so everything will be even clearer. But up to now, the important thing to notice is that we do not have points in the sensor, in the reference frame of the sensor, as it was in the previous exercise. We only have direction of points. Now, having directions in the 3D space is equivalent to having an azimuth and elevation angle. And azimuth and elevation angle describe the manifold of the sphere in the 3D, of the two-dimensional sphere. And the two-dimensional sphere, the manifold of the two-dimensional sphere is called, is indeed S2. So we have that in this case we only have direction vectors, meaning that we have an azimuth and an elevation, azimuth and elevation. Now, these elements of S2, which is the set of the joint of azimuth and elevation, can be over-parameterized as vector of R3, meaning that instead of considering these two angles, we can consider directly a vector in the 3D space. Now, of course, azimuth and elevation are associated to an infinite set of vectors, because all the scaling factors applied to this vector allows us to get the same azimuth and elevation values. This is why we talk about direction vectors, and this is why, in order to represent elements of S2 as elements of R3, we impose that the norm be equal to 1, so that we remove the degree of freedom coming from the scaling that we can apply to this vector, still obtaining the same azimuth and elevation. So in this case, what we do, our prediction function is a little bit more complex than in previous exercises, because given a point pi in the word frame, in order to obtain the direction vector in the reference frame of the sensor, what we do is we apply the transformation from word to sensor, which is given by the rotation r and the translation t, and then we normalize this, because we want to eliminate the degree of freedom given by the scaling by considering unit norm vectors. Okay. What you need to remember from this slide is, in particular, of course, the prediction function. And you need to tell me if this idea of representing azimuth and elevation as direction vectors with unitary norm makes you, if you feel comfortable with it. Okay. One student says yes, and the other one.
50% of the class
Okay.
says yes.
Okay.
We have apparently two.
Okay.
Two at home, because I have two people talking in the chat, but the point is that I have many playbags, so probably.
Okay.
Stopping in different.
S2 is S2 squared.
No, it's the sphere. The unit sphere. It's the name. It's the name of the manifold of the unit sphere. So it's the domain of the unit vectors, which is the unit sphere.
Okay.
Just what mathematicians like to do. That's also S3.
Yes, S2 is the domain of the sphere. It's not the SO2, it's S2. It's the manifold of the sphere. And, okay, so it's the manifold which represents the surface of the sphere. And of course, in that case, as the radius is fixed, then points are only, then you can select a point by only specifying the azimuth and the elevation. Okay, so I guess we can move on with the usual way of formulating the problem. So we start with the state space and then move to the measurement space and to the prediction function. So the state space is a transformation from the word frame to the sensor frame. So it's an element of SC3, and it's composed by a rotation matrix and a translation vector. We are not considering the scaling in this case. The transformation from word to sensor is a regular homogeneous transformation. Then we need to define a Euclidean parameterization, and R6 is very convenient in this case, as we have already seen in the previous slides. Then finally, we need to define a box plus operator. Again, the vector to transform is convenient. Okay, this should be clear, so I guess I can move on with the measurements, which is much more interesting. So the domain of the measurements, it's a manifold. It's a manifold because the measurements belong to S2, which is the manifold of the sphere in 3D. Again, points lying on the sphere can be selected by an azimuth and an elevation angle, or by their 3D coordinates. But this parameterization using 3D coordinates is an over-parameterization of the problem. And because indeed we already know the radius is known, so azimuth and elevation are sufficient, or a direction is sufficient. Meaning that instead of working with these three coordinates, we can consider all the vectors with unit norm. That is what we have already said in the previous slide. Then, as measurements are elements of a manifold, we need to define a box minus. Again, the Z1 box minus Z2 means computing the chart around the Z1, projecting Z2 onto this chart, and then measuring the distance between Z1 and Z2. In principle, we should get a relative angle on azimuth and elevation, and we should do this by representing Z1 and Z2 as rotation matrices, and then combine them using the usual product of rotation matrices. So an idea for doing this would be to construct a rotation matrix using x-axis parallel to the direction z, y-axis lying on the plane z equals 0 and orthogonal to the x direction, and then z-axis normal to the two of them. And once you are able to do this for both Z1 and Z2, you can compute the rotation difference by using the usual product of rotation matrices, in particular by doing the inverse of R2 times R1. This would be, say, the way to operate staying in a manifold formulation in a manifold space, because we are using rotation matrices. But we can do better than this. Say not better because it's an approximation, but easier to implement. We can simplify the problem by treating Z as if it were Euclidean, which means instead of retrieving a rotation matrix out of the vector Z, we use Z as Euclidean vector, Z1 and Z2 as Euclidean vectors, and compute the distance between these Euclidean vectors. Now, the problem is that in this way, we are not operating on a geodesic distance. We are using a chordal distance. This is why it's an approximation, because we are not computing the distance on a geodesic, we are computing a chordal distance. But it is very convenient, of course, because if you treat Z in this way and you work with a direction vector, then instead of using a box minus, you simply use a minus, and computing the Jacobian is very simple. Okay, now it could be that it's not too clear at this point, but it will be clearer in the next slide. Anyway, is the concept, say, clear, or at least do you like this? Okay. So we can move to the error function. As I was mentioning, if we consider hi of x as the direction vector, which is a normalized vector, then we can use the regular minus instead of the box minus. And we have that the error function, again, is the difference between the prediction of the measurement given the current estimate of the state and the actual measurement Zi. Now, as we were mentioning in the first slide of this exercise, we have that the Z, which is the direction vector of the point, can be obtained from the point in the word by obtaining the point in the sensor frame, applying the rotation matrix R and the translation matrix T, which identify the pose of the word in the sensor frame, and then we normalize this in order to work with unitary vectors to eliminate the degree of freedom coming from the scaling factor. Okay, so once you have this, you can compute also the measurement, the prediction function in x box plus delta x. Nothing weird. It's the usual ICP in 3D. And you can recognize the delta r and the delta t, and the pi prime, which is the point in the sensor frame. And now we are at the end. We only missed the computation of the Jacobian. So if this is clear so far, I can go into the computation of the Jacobian, and then you have time to solve the exercise. Okay.
Say something about the chain rule of the normalizer.
Yes. No. Yes. I was leaving this for now. Okay. So now, in order to compute the Jacobian of this function, what we do is we apply the chain rule. In particular, in this case, we have the normalized function, which is concatenated with the ICP function, the application of a transformation, homogeneous transformation to pi. Then what we can do is we can compute the derivative of the normalized function with respect to p, and then the derivative of the argument with respect to the state. In particular, since we're using the least squares on manifold formulation with respect to the perturbation of the state. So what we do is we first compute the derivative of the normalized with respect to p, and then compute the derivative of the argument of the normalized with respect to the state. Now, the derivative of the normalized function should be computed using the usual square of the denominator, and then at the numerator you have the derivative of the numerator times the denominator non-derived, and so on. But
like a question, like how big is the Jacobian of the normalized function? Question for the boss.
Yes. How big is the Jacobian of the normalized function?
Dimensions. 3. 3 by what? What's the size of the domain of the normalized? What's the size of the codomain?
3 by 3.
Yes.
3 by 3.
Okay, so here in class they said the dimensions correctly. The dimension of the Jacobian of the normalized is 3 by 3, because the normalized, the measurement is 3-dimensional. The normalized, it's a normalized vector, 3D vector, so it's again a 3D vector. So the derivative of normalized with respect to p is as high as 3 and as large as the dimension of p, which is again 3. Then this, you can do it by yourself, and then you have the chain rule. And as you can see here, we have the derivative of the normalized times the derivative of the ICP, the derivative of h ICP. Because the remaining part of the function is the usual ICP prediction function, so you can directly write the derivative of the ICP prediction function. Otherwise, you can do the computations by yourself, step by step. Okay, so while you revise this for a second by yourself, I show you the exercise. And see here, in your folder called source octave, and you have the 23b, and then you have a norm and exercise. And what we ask you to do is to have a look at the test file and fill the to-dos, like the measurements. But be careful, because there are some mistakes. So we ask you to spot these mistakes and correct them. And then you have this error and Jacobian norm, where in this case we leave you do the exercise by yourself. So no to do, at least it is one big to do. Okay. So this is all for now.
Have fun.
Yes.
We have half an hour.
Have fun. so the students in remote can see me. And we will go through the solution very quickly, and then I will push the solution after the lesson so you can check it by yourself offline. So here we have the solution on the left and the exercise on the right. So the first to do was here when we were asking you to generate the set of measurements. Now, the set of measurements is obtained from the set of points in the sensor frame by normalizing them. Okay, I will take the slides very quickly so that you can see what I mean. You have the set of points in the word frame. This set of points is called the moving set in your code. And then you have to take this set, bring this to the sensor frame, and then normalize these points in order to obtain the measurement. And this is exactly what is done here, where we have the moving cloud, which is again the set of points in the word frame. We generate the fixed cloud by applying the transformation from the word frame to the sensor frame. Again, we rotate by R and translate by T. And then once we have this fixed cloud, which we call fixed because it's the one that we are not going to move, what we do is we compute the norms and the inverse of the norms, and then once we have the norm for each of these points, then we simply multiply the cloud by the inverse of these norms in order to normalize the points in the cloud. Yeah, notice that in this very compact, there are more ways to do this, but this is probably the most compact one because we are using this dot product of MATLAB. I mean, it's not the dot product within vectors, it's the element by element product, which we can represent in MATLAB using this dot and then star, dot and then division. Okay, so if you use this this MATLAB dot properly, then you can write these lines of code very compactly in order to obtain the set of measurements. Anyway, how you do this, it's just a matter of an implementation. The important thing is that you know that the moving cloud should be brought to the sensor frame by using the ground truth pose and then normalized. Okay, this is the important thing. Once you know and you understood this, everything is just coding. Okay, but anyway, I will give you the solution so that you can use this compact notation, learn it, and use when you need it. So, after this part is completed, then you can move to the Icp Loop, where you were asked to fill the dimensions of H and of B. And of course, as we have seen in the slides, in this case the state belongs to SC3, so that its local perturbation is a 6-dimensional vector. We are using a 6-dimensional perturbation for the Euclidean parameterization, so that the H matrix will be 6 times 6, and the B vector will be 6 times 1. Remember, indeed, that H is J Jacobian transpose times omega times J, so it is as large as the height of J. as large as j, and we remember that j is as large as 6. Okay? So once the dimension of the H matrix and of the B matrix are filled correctly, then you could move on with this for loop on the number of measurements and spot the errors. There was one error here and another one was here. In particular, as far as the computation of H is concerned, we have that, first of all, dimensions do not match because we are computing J omega J transpose instead of J transpose omega J. But, as you remember, omega is 3 times 3 because it is as big as the measurements, while J is 3 times 6 because it is as large as the dimension of the perturbation, so that this product here cannot be solved. So that MATLAB would complain if you try with this expression of H. And anyway, you remember the theory and you remember that the correct formula is J transpose omega J. This is not the only error. There is one more, which is that the plus is missing. Indeed, if, as you may remember from the algorithm wrap-up, we build the H matrix by summing the contribution coming from the measurements, so that here there should be a plus. And summarizing, in line 43 of the solution, we have H plus equal J transpose omega J. As far as the computation of the B vector is concerned, again, we have the plus missing and we have E transpose omega J in place of J transpose omega E. Then everything else is correct. Please, as usual, check that we are using the box plus instead of the regular plus. So here what we do is we compute the perturbation by solving a linear system with coefficients H and B, and then apply the perturbation to the current estimate of the state by using the box plus operator, which in this case is a vector to transform. Okay, so this is all for the test norm registration file, and if there are no particular questions, then we can move to the error and Jacobian. It's perfectly normal that you're still missing something, or you just didn't notice the plus, for example. But at least you should be confident with the theory. For example, you should be confident with the dimensions of H and B. Okay. So, if you do not have any complaints, then you can move with the error and Jacobian. Okay. So, I am moving to the error and Jacobian function. Here again, this function takes as input the current estimate of the state, a point in the world, and a measurement, z. And what we do is we predict the point in the sensor frame from the point in the world frame by applying the homogeneous transformation x corresponding to the current estimate of the state. Then what we do is we obtain the measurement, the prediction of the measurement, by normalizing this p hat. Indeed, we recall that in this case, the measurement is not simply a point in the sensor frame, but it's the normalized version of this point. It's the normalization of this point. So what we do is the z hat is the division of p hat by its norm. Then once we have the prediction of the measurement, we can compute the error. And having done this, we can compute the Jacobian by applying again the chain rule. As you have seen in the last slide, which is this one, which I will put here on the right, you can see that we compute the Jacobian as the product of the Jacobian of the normalized function computed in pi prime, which is the argument of the normalized function in the prediction function, times this Jacobian here, which is the usual Jacobian corresponding to the Icp measurement function. So what you do is you compute your JICP by blocks. You compute first the first block, which is an identity block of dimension 3. Then the second one, which is minus the skew symmetric matrix in p hat. And then once you're done with this, you can write down the Jacobian as the product of the Jacobian of the normalized function computed in the argument of the normalized, which is p hat, and then multiply this by the Jacobian of the Icp function. Okay. So the only thing to note is that you could write down your own J-normalize or use the J-normalized function in the geometry helpers 3D. Okay. If everything, no, I will only show you the result. So octave test normal registration. And you can see that the evolution of the chi-square rapidly goes to 0. As usual, we are using a synthetic data set with no noise on the measurements, so we expect the error to go to 0 by applying least squares. There are no wrong associations because, again, we have an ordered vector and generate an ordered vector of measurements. And everything is synthetic in its context, so we expect the error to go to 0. No outliers and so on. Okay, here you see also the evolution of the chi as the iterations proceed. So you can see that in the first one it was 1, and then it rapidly goes to 0, and let's say 1 e to the minus 19, e to the minus 32, so it's 0. Okay, I guess we are done. So if you have any questions, please write an email as we are closing the streaming right now. And okay, here in the class everything is okay.